Okay, so this video is on deriving the derivatives of exponential and logarithmic functions, and then we're going to work through some examples. So if we're trying to take the derivative of just a general exponential function, so where base is a, so a raised to the x power, let's start with attempting to use the limit definition of the derivative, which remember is the limit as h approaches 0 of the difference quotient. So for this function, we would have the limit as h approaches 0 of a to the x plus h minus a to the x all over h. And then by one of the properties of exponents, if we were to separate a to the x plus h, so that it was a to the x times a to the h. Okay, right? Because when we have the same base and we're multiplying, we just add the exponent. So I just went in the reverse. So I separated that back into a product. Where now I can actually factor out an a to the x in the numerator. So we have a to the x times a to the h minus 1 all over h. And a to the x we can actually treat as a constant and pull it up front, because if we're taking the limit as h approaches 0, so nothing would happen to a to the x when we take the limit. It would behave like a constant. Okay, so we're going to take a time out for a sec and then go back up to the original limit. And let's think about if we wanted to find the slope of the tangent line to this function at x equals to 0. That would be in this limit replacing all of the x's with 0. So we would have a to the 0 plus h minus a to the 0th all over h, which when we simplify that is a to the h minus 1 all over h. Okay, so this is the derivative of f evaluated at 0, which ends up corresponding to this limit down here, where we're trying to find the derivative of the function a to the x. So what this says is that f prime of x is equal to a to the x times f prime of 0, which is weird because that says that you need the derivative evaluated at 0 in order to find the derivative. So that just doesn't work. So we're going to have to put that on hold. We're going to come back to finding the derivative of a to the x. Okay, so here are some definitions of e that we're going to reference in a second. All right, so for e to the x, if we were to try and find the derivative of e to the x evaluated at 0, it would be the limit as h approaches 0 of e to the h minus 1 all over h. This is the derivative evaluated at 0. Well, that limit, if we reference our definitions up here, this is one of the definitions for e. So f prime of 0 is equal to 1. So that means that if we're down here, right, we ended up getting stuck at f prime of x equals to a to the x times f prime of 0. Well, if we're using e as our base, so let a equal to e, that would say f prime of x is equal to e to the x times f prime of 0, which is 1. Therefore, the derivative of e to the x is actually just e to the x. That one's going to be really easy to remember. Derivative of e to the x is just itself. Okay, so now we're going to come back to finding the derivative of a to the x. And to do this, we're going to use a property of logarithms where we're going to rewrite, so this is using a property of logarithms. Where we're going to rewrite a as e to the natural log of a. Right? Same bases there, that's just actually equal to a. So f of x, we have our function f of x equals to a to the x, which is now equal to e to the natural log of a raised to the x power. And that's a power raised to a power, so that we multiply the exponents. So that's natural log of a, e to the natural log of a, not x, times x. Where natural log of a is just a constant. Okay, so f prime, to find f prime, we're going to treat e to the natural log of a times x as a function and composed with another function, right? So we're going to think of e to the x as the outside function. Here, I'll use colors for this. So it's e to the x as the outside function, and then natural log of a times x as the inside function, so that when we find the derivative, we're thinking chain rule. So the derivative of the outside function is just e to the x, and we leave the inside function alone. So we get natural log of a times x. And then times the derivative of the inside function. Well, natural log of a times x, natural log of a is just a constant, therefore the derivative is natural log of a. We rewrote a to the x as this, e to the natural log of a times x. So the derivative of a to the x is actually a to the x times the natural log of a. Okay, this can be derived, but we're just going to treat it as a fact. Okay, so in order to find the derivative of the natural log of x. So recall that f of x equals e to the x and g of x equals to ln of x are inverses of each other. Okay, therefore, using this fact up here, g prime of x has to be 1 over the derivative of the inverse, which is the derivative of e to the x, remember it's just e to the x, evaluated at the function. Well, thinking about properties of logarithms, this is actually just 1 over x. So therefore, when we take the derivative of natural log of x, it's 1 over x, but remember, the domain of natural log of x is actually x greater than 0. So we have to say for x greater than 0, 1 over x is the derivative. However, if we take the derivative of the natural log of absolute value of x, which has a domain of all real numbers except 0, then the derivative is 1 over x for all real numbers except for x equal to 0. And this will become more important when we are talking about antiderivatives. So just kind of keep that in the back of your head. But for now, the derivative of natural log of x, you need to know, is 1 over x for x greater than 0. Okay, so to find the derivative of log base a of x, we're going to use change of base formula. to rewrite log base a of x as natural log of x over natural log of a. So taking the derivative of log base a of x is going to be equal to taking the derivative of natural log of x over natural log of a, because they're equivalent. Natural log of a is really just a constant, so I can pull out 1 over natural log of a and multiply it by the derivative of ln of x, which we just saw was 1 over x. Ooh. So the derivative of log base a of x is 1 over x times natural log of a. There's a summary here. I suggest you guys memorize it. E to the derivative of e to the x and natural log of x are pretty easy to remember. And then you could always derive them, but I think it's pretty easy to just remember these, memorize these like the derivatives of the trig functions. So if we want to differentiate the following functions, let's switch colors. Finding f prime, the derivative of 3 to the x will be 3 to the x times natural log of 3. Right, if we reference back up here. Okay, and then we'll have minus 4 times the derivative of log base 2 of x will be 1 over x times natural log of 2. And just to rewrite that, okay, so that's it. That's the derivative of f. Finding g prime. The derivative of 5e to the x is 5e to the x. To find the derivative of the next piece of the function, well, let's think of 3x cubed as one factor and natural log of x as the other factor. So we actually have to use product rule here. So I'm going to put it in put product rule in brackets. So we'll have 3x cubed times the derivative of natural log of x, which is 1 over x, plus the derivative of the first factor, which is 9x squared, times ln of x. And when we simplify, we'll have 3x squared, and I'll leave that as 9x squared times natural log of x. Looks kind of yucky, but it was really not so bad to find. All right, we are going to have to use quotient rule to find the derivative here. So we're finding y prime using quotient rule. So I bring the denominator up times the derivative of the numerator, which would be 6e to the 2x times 2, thinking chain rule, minus the numerator times the derivative of the denominator, which is just 3e to the x, all over the denominator squared. Okay, so cleaning that up, we're going to distribute, that's 12 times e to the 2x. We're going to distribute that into 3e to the x. So that will be 36e. Since we have the same base and we're multiplying, we add the exponents to get 3x. Okay, plus 12e to the 2x. And then we'll have minus 18e to the 3x again when we add the exponents. And then we'll have like terms that we can combine to get 18e to the 3x plus 12e to the 2x all over 3e to the x plus 1 squared. All right, our last example, we need to find the equation of the tangent line to the function f at x equals to 1. So we think about, what do we need for the equation of a line? We need a point and we need a slope. Well, we have the x coordinate of the point, so we still need the y coordinate. And we can find that y coordinate by evaluating the function at 1. Remember, anytime you take the logarithm of 1, it's just 0. So we have our point and we need our slope, but we need the derivative in order to find the slope of the tangent line. We need to use product rule. So e to the 3x times 1 over x times natural log of 2, right? That's the derivative of log base 2 of x, plus e to the 3x times 3 times log base 2 of x. Just cleaning that up a little bit. E to the 3x over x times natural log of 2. Make it look nicer before we use it. Okay, so now we can actually find the slope of the tangent line by substituting 0 in for x. No, not 0. We're not substituting 0 in for x. I'm sorry. I had to think about that for a second. We're substituting 1 in for x. That makes more sense. Remember, the log of 1 is 0, right? 2 to the 0th power to give us 1. So our slope is just actually e cubed over a natural log of 2. So writing the equation of the tangent line, we'll have y minus 0 equals e cubed over ln of 2 times x minus 1. So that's the equation of our tangent line in point slope form. Tangent line. Okay. And the homework is just practicing finding the derivatives of these types of functions. We will do more practice in the next class.